Welcome to the mathacademy.net channel, and welcome to our series on deconstruction in mathematics education. My name is Bo. Today we address the question, mathematics is hard, or is it? We begin with primary school, and welcome to our guest, Alan, who uses deconstruction in his work.
Thank you, Bo.
Alan, what does deconstruction mean to you?
Well, Bo, to me, deconstruction means what it says: destruction and reconstruction. It is the method that is used by postmodern skeptical thinking that dates back to the ancient Greek sophists. The sophists warned against patronization that is hidden in choices that are presented as nature. So to avoid hidden patronization, false nature must be unmasked as choice. And to deconstruct then means to discover or to invent alternatives to choices that are presented as nature.
Thank you, Alan. Do you have a short answer to tonight's question?
To me, the short answer to the question, mathematics is hard, or is it, is that mathematics is not hard by nature, but by choice. Mathematics is made difficult by its missing links.
And what do you mean by missing link?
I use the term missing link to indicate that mathematics has lost its links to its root, the natural fact, many. However, if these links are established again, then mathematics will once more become a science about many. And accepting it as a natural science will make mathematics easy and accessible to all, instead of difficult and accessible only to few.
So, Alan, what is the first missing link?
Well, Bo, the first missing link is the total. To deal with many, we total, that is, we ask the question how many. And the answer is given by the total. That is why we use the word algebra, that means to unite, in Arabic. Thus all mathematics statements should begin with its subject, the total, and specify what the total is. The first step is to represent the total in three ways: by physical sticks, by graphical strokes, and by spoken words. Thus 4 things can be represented by 4 sticks on the table, and by 4 strokes on a paper, and by the word for. Now we can write that T equals stroke, 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 stroke.
That is what the Romans did, isn't it?
Indeed it is. But the Arabs went one step further by using icons. They united the 4 strokes into one single symbol consisting of 4 strokes. Thus they transformed 4 ones into 1 fours.
But isn't 4 ones and 1 fours the same?
Well, Bo, 4 ones means that you count in ones, so that 1 is the unit. Whereas 1 fours means that you count in fours, so that 4 is the unit. And that you count by bundling and stacking the total in fours. Thus rearranging sticks and strokes into icons is the second missing link. If we write the digits in a less sloppy way, we can see that there are 5 sticks and strokes in the 5 icon, and 6 strokes in the 6 icon, etc.
But why do the icons stop at 10?
We count by bundling, but we never use the bundle icon. If we count or bundle in 5s, we count 1, 2, 3, 4, bundle, 1 bundle, 1, 1 bundle, 2, etc. Or in a shorter way, 1, 2, 3, 4, 10, 11, 12, etc. Thus we do not use the 5 icon. Likewise, 10 does not need an icon when counting in tens. In this way 10 is the only number with its own name, but without its own icon. This makes 10 a cognitive bomb, since 10 is the follower of 9, but 10 is the follower of 4, when counting in 5s. So 10 is not 10 by nature, but by choice of the bundle number.
So what is the third missing link?
The third missing link is cup writing. First we count the sticks or strokes by bundling them in, for example, fours. Then we can place the bundles in a left bundle cup, and the unbundled in a right single cup. We don't have to place the physical bundle. For each bundle we just place a stick in the bundle cup. Now we can use the icons to write the total, using a decimal point to separate the bundles from the unbundled. In this way a total of 6 ones can be counted in fours as 1 4 and 2 ones, and written as 1.2 fours. So a natural number includes a decimal point to separate the bundles from the unbundled, and a unit.
And what is the fourth missing link?
The fourth missing link is recounting, or changing the unit. Thus a total of 7 ones can be recounted in fives as 1.25s, or as 1.34s, or as 2.13s, etc. If counted in tens, 7 ones becomes 0.7 tens. However, we only write 7, leaving out the unit, and misplacing the decimal point, 1 placed to the right. This may be okay in business, but it creates learning problems in schools.
I guess that recounting is done by debundling and rebundling?
Yes. Recounting can be done manually by debundling and rebundling. However, counting in fours means to repeat taking away 4, that is, dividing the total by 4. So the counting result can be predicted by a recount formula saying that the total t can be bundled in b's, t divided by b, times. So t is t divided by b, b's, which is the same as t divided by b, times b. Thus the recount formula predicts that recounting a total of 8 ones, in fours, gives 8, divided by 4, of the fours, which is 2 fours.
So recounting is another word for shifting units?
Yes. To shift the unit means to recount. The tradition calls it proportionality or linearity. Shifting unit is the core of mathematics, and easy to learn as recounting. However, the tradition avoids recounting. Instead it insists that counting only takes place in tens, and that the decimal point is misplaced, and that the unit is left out. Thus what is called natural numbers are in reality highly unnatural. Many learning problems may disappear by respecting that, of course, any natural number has a decimal point and a unit. And by postponing counting in tens as long as possible in grade 1.
And then what is the fifth missing link?
The fifth missing link is predicting numbers by calculations. To recount 4 5s and 6s manually, first we must count up the 4 5s. Then we must debundle them in 1s. And finally we must rebundle them in 6s. This is a long and tiresome job. However, if we use the recount formula and a calculator, we can predict the result to be 3 6s and the rest. And the rest is found by removing the 3 6s from the 4 5s. So the result of recounting can be predicted by a calculator, using division and subtraction. Predicting recount results shows the very essence of mathematics. Mathematics is our language for number prediction. Experiencing its predicting ability yourself may remove many motivation problems.
Alan, you say that mathematics is a language.
Yes, Bo. We describe the world by words and numbers, so we have 2 languages. Our word language combines letters to words, and words to statements that describe the world. Our number language combines digits to numbers, and numbers and operations to formulas that predict the world. However, a language also has a meta-language, a grammar. A language is like a 2-level house, a language house. At the lower level the language describes the outside world. And at the upper level the grammar describes the language. Meeting a language before its grammar makes it easy to learn, as in the case of the word language. Meeting a language after its grammar makes it difficult to learn, as in the case of the number language, which claims that its grammar, mathematics, must be learned before it can be applied.
But clearly, to apply mathematics, you must first learn mathematics.
Here we are seduced by our words. If we talk about rooting instead of applying, the logic is the opposite. Of course the root comes before what it roots. And the roots of mathematics can be seen in the names algebra and geometry, meaning earth measuring in Greek, and uniting in Arabic. So presenting a grammar before its language is not nature, but choice.
Alan, can you give more examples on how mathematics predicts?
Certainly, Bo. As a matter of fact, operations are invented to predict numbers. Thus 3 plus 5 predicts the result of counting on 5 times from 3. And 3 times 5 predicts the result of adding with 3, 5 times. And 3 to the power of 5 predicts the result of multiplying with 3, 5 times. Furthermore, we saw that digits are icons that contain the number of strokes they represent. Likewise, Operations are also icons that show the counting processes they represent.
Can you please specify that?
I would like to. Taking away 4 is iconized as a horizontal stroke showing the trace left when dragging away the 4. Taking away 4 many times, that is, taking away 4s, is iconized as an uphill stroke showing the broom sweeping away the 4s. Placing a stack of 4 singles next to another stack is iconized as a cross showing the juxtaposition of the 2 stacks. And building up a stack of 3 4s is iconized as an uphill cross showing a 3 times lifting of the 4s.
From the recount formula, it seems as if division and multiplication come before addition and subtraction.
Indeed they do. After recounting is predicted by a rebundle formula, using division and multiplication, we can predict the unbundled by a restack formula, using subtraction and addition. So the natural order of operations is division, multiplication, subtraction, and in the end, addition. This is in contrast to the tradition that reverses the natural order, which create yet more learning problems. And that brings us to the 6th missing link, that operations, and especially addition, can be both soft and hard. This link is missing both in primary school and in secondary school.
Okay, Alan. So next time we will hear about that. Can you shortly mention what the other missing links are?
Yes, Bo. The 7th and 8th missing links are reversed calculations and per numbers.
Thank you, Alan. This time we have heard about 5 missing links, the total, from sticks to icons, cup writing, recounting, and predicting calculations. Next time at the mathacademy.net channel we will look at deconstruction of secondary mathematics and hear about the 3 remaining missing links.